So in video 4, we're going to look at an application of an exponential growth model. So continuous growth, we have as part of a lab experiment, a biologist needs to grow a culture of 250,000 bacteria, which are known to double in number every 18 hours. If he or she begins with 1,500 bacteria, determine the number of hours it takes for the culture to produce the 250,000 bacteria. So if we assume that the bacteria grow exponentially, then we can model their growth with the exponential growth model. Q equals Q naught e to the RT. This is the continuous exponential growth model. And then we can kind of catalog the information that we're being told in the paragraph. We're told that we begin with 1,500 bacteria, which means at time equals 0. There are 1,500 bacteria present, and in the exponential growth model, Q naught is the initial number of bacteria. So this piece of information tells us that Q naught equals 1,500. We are also told that the doubling time is 18 hours, which means in 18 hours there are going to be twice 1,500 or 3,000 bacteria present in 18 hours. And we want to know how long it will take to generate or produce 250,000 bacteria. So ultimately this is the question we're trying to answer right here. So first step is we know what Q naught is, so let's update the model with Q naught. Q equals Q naught, the initial number of bacteria is 1,500 times e to the rate times time. We need now to figure out what R is, the rate, and we do that by using the doubling time. We know that in 18 hours we will have Q equals 3,000 bacteria, so replace Q with 3,000 equals 1,500, e to the rate times time. Time will be 18 hours. We need to get the rate out of the exponent position, so we need to isolate the exponential base e so we can apply the natural log to both sides and cancel it. So we're going to divide by 1,500, and if we do that we'll get 3,000 divided by 1,500 is 2. So you can see the Q naught canceling out of the equation just like it did with radioactive decay. The doubling time doesn't depend on the number of bacteria that you start with. We need to get the R out of the exponent position, so we're going to take the natural log of the base e exponential, take the natural log of both sides. The natural log will cancel the base e exponential because they're inverse functions. That's going to leave us with the exponent equaling the natural log of 2, and then we can divide both sides by 18 in order to solve for R. R times 1 is just R, and R equals the natural log of 2 over 18. And then we want to go back to our model and update it now and get a final model. The final model is the quantity of bacteria over time will equal the initial number of bacteria times e to the R, but R is just the natural log of 2 over 18, and we need to multiply that rate times time. And now we're in a position to figure out how long it's going to take to generate or grow our 250,000 bacteria. We don't know time, but we do know how many bacteria we want. So we'll replace Q with the 250,000. And we don't know the time because that's what we're trying to figure out. So time just sits here waiting to be dug out of the exponent. So we'll need to isolate the base e exponential expression again. So we'll divide both sides by 1,500. We'll divide by 1,500 on the left side as well. This is going to equal 1 times e to the natural log of 2 over 18 times time. We're going to lose a couple of the 2's. 5 will go into 15 3 times. 5 will go into 25 5 times with the 2 zeros left over, so we get 500 over 3. And now we can take the natural log of both sides over 18 times time, because the natural log or log base e will cancel the base e exponentiation, leaving us with the stuff in the exponent position, which is just the natural log of 2 over the 18 times time. And we still have the natural log of 500 over 3 on the left-hand side. To get t by itself, we'll multiply by the reciprocal of its coefficient, so multiply by 18 over the natural log of 2. We need to do that on both sides, so multiply by 18 over the natural log of 2. These will become a 1, so we're going to be left with time, and we can approximate time now by putting this into the graphing calculator or into any calculator. It doesn't have to be a graphing calculator. Let's keep that. Be patient for one moment. Slide it off to the side. Grow the page larger so we can see it. So we need to input into the calculator 18. So we'll clear the screen here. So 18 times the natural log of 500 divided by 3. Close that parentheses. Now divide by, we have natural log of 2 in the denominator, so we need to divide by the natural log of 2. Close that function. Enter, and we get about 133 hours will be needed to get to the 250,000 bacteria. So we're going to need about 133 hours of time.